Hello everyone, welcome to Calculus Lecture 9, and today we'll be talking about the chain rule. So we've talked about this before, but here's the general formula. So say we have two functions, f and g, and then we have their composition, so that's f of g. Or sometimes you can write like f of g of x like this with parentheses. It just means you're applying g and then you're applying f. Remember, with function composition, we always read right to left. It seems maybe a little unintuitive, but it's because of this notation. It's just that we're applying g and then we're applying f to it. Now the chain rule tells us that f of g prime of x, the derivative of a composition, is given by this formula. So we take the derivative of the outer function f, so that's the second function, and then we apply it to g of x. And then we multiply by the derivative of the inner function, so times g prime of x. And then we also have another version of the chain rule, which is pretty much the same thing. And so what that tells us, if we have y is some function of x, or actually, let's put it this way, y is some function of u, and u is some function of x, then of course y is also a function of x, because you can write u as a function of x and then y as a function of u. And so we can look at dy dx, the derivative of y with respect to x, and that's going to be equal to dy du, so we're going to differentiate this guy, times du dx, which is what we get when we differentiate this guy. And so these are just equivalent ways to state the chain rule. And it's actually pretty simple once you get used to it, but the notation can be a little awkward at first. Let's do some examples. Here's one problem. All right, find the derivative of sine 2x with respect to x. So I'll just pause for a moment and see if you can figure that out. Okay, so I'm going to do this both ways just to demonstrate. You might find that one way clicks more for you than the other. So the first way we can do it is using this rule. So f of g prime of x equals f prime of g of x times g prime of x. So let's figure out what these functions are. So we want to write this as a composition. So the inner function is 2x, and then the outer function is sine. So let's write this. So we want g of x equal to 2x, and f of x equal to sine of x. And we can check that the composition works as we want it to. So f of g of x is f of sine x, because g of x is, or sorry, f of 2x, because g of x is 2x. But what is f of something? F of something just takes the sine, so that's sine 2x. So it's exactly what we want. And so now the derivative of sine 2x is going to be f of g prime of x. All right, which we're going to use this formula now. So that's f prime of g of x times g prime of x. So what is f prime of g of x? So f is sine. So the derivative of sine is cosine. So f prime of anything is cosine of that thing. But we're applying it to g of x. We're applying it to 2x. So this is going to give us a term of cosine of 2x. Times g prime of x. So g of x is 2x. The derivative of that is just 2. So we're just going to multiply this by 2. And that's our final answer, 2 cosine 2x. Now we can do this the other way as well. So we have sine 2x and we can do our u substitution. Say y equals sine 2x, then what we're trying to find, f prime of x is equal to dy dx. That's what we want to find. And we can write u as the sinc function. And then y is equal to sine u. So it's basically the same thing, whichever notation you prefer. Dy dx is equal to dy du times du dx. And now we can solve this. So what's dy du? That's the derivative of y with respect to u. So we differentiate this. So we get cosine u times du dx. So now we differentiate this. So that's going to give us 2. So it's 2 cosine u. But what is u? U is equal to 2x. And we substitute. And so that's equal to 2 cosine 2x, which is exactly the same answer we had before when we did it using this formulation of the chain rule. All right, let's do another example. So let's find the derivative of x squared plus 4x. And I'm not going to label this y because y is being used as another variable. So I want to find, I'm going to say z equals this. And x equals 5y cubed. And I want to find the derivative of z with respect to y. So see if you can work this out. The variables are a little bit unusual, but see if you can still make that work and formulate the chain rule accordingly. In this case, usually u was your intermediate variable. In this case, x is going to be the intermediate variable. All right, so in this case, I really, really do want to use the second formulation. That's just going to make it a lot easier with the notation. And then I will also do it with the first formulation. But let's first see how this works. So we're trying to find dz dy. So now using the chain rule, that's dz dx times dx dy. And notice that the variables don't really matter that much. Like we used to use u for x and y for z, and maybe x used to be our y, so it's all switched around, but that's fine. The easiest way to remember this is you have your dx or whatever cancels. Doesn't exactly cancel, but that's basically how you can think of it. Now, what is dz dx? Well, now we differentiate this one. So we're just taking the derivative of x squared plus 4x with respect to x. So that's going to give us 2x plus 4 times dx dy. So now we're going to use this, and we're going to differentiate with respect to y. So dx dy will be 15y squared. All right, and now we have one more step. We actually want this in terms of y, because y is in the denominator here. So we want to substitute this x needs to be in terms of y, but we can do that because we know that x is 5y cubed. So let's substitute. We're going to get 2 times 5y cubed plus 4 times 15y squared, right, which is 10y cubed plus 4 times 15y squared. And I think that's simplified enough. Now we can do it the other way. So what is our inner function and what's our outer function? Well, in this case, this is the outer function, the x squared plus 4x. So this is taking the place of our f. F of x is equal to x squared plus 4x. And then g of x equals, g of y equals 5y cubed, or g of x equals 5x cubed, whichever formulation. If you're okay with using the same variable, that's fine, or you can use a different one. And then the composition, we because x is equal to 5y cubed, we could substitute that. And so the whole thing is going to be f of g. And then we're looking at f of g prime of y. So f of g prime of y, from the formula, that's f prime of g of y times g prime of y. All right, so what's f prime of g of y? So f is x squared plus 4x. The derivative of this, and we're pretending we're plugging g of y into it, but let's just take the derivative first. So that's going to give us 2x plus 4, and then we're going to plug g of y into it. So g of y is 5y cubed. So this is going to give us 2 times 5y cubed plus 4. Times g prime of y, and so now we're just going to take the derivative here. So that's 15y squared. And we can see that that's the exact same answer as before. All right, let's do another example. And I'm just going to do it in one way, whichever way seems easier for the problem. So let's do y equals 2 times the natural log of v, where v equals u cubed. All right, and we want to find dy du using v as an intermediate variable. So once again, I'll just pause for a moment and see if you can figure it out. All right, so let's use the chain rule. So we have dy du equals dy dv times dv du. All right, so let's work this out. So dy dv, we're just going to be differentiating this. So this is going to be equal to 2 times 1 over b. Because the derivative of the natural log is 1 over x. All right, times dv du. Now we're differentiating this with respect to u. So that's times 3u squared. All right, so this is 2 over v times 3u squared. And then we want to substitute for v in terms of u. So now v equals u cubed. So that's going to be 2 over u cubed times 3u squared. And there's some cancellation here as long as u is non-zero. So that's going to give us just u over here. So that's just going to be 6 over u. So we multiply the 2 and the 3 there. And so that'll be our final answer. All right, let's do a couple more examples. Let's do f of x equals 6x squared plus 7x to the 4th power. See if you can find 3 different ways to do this problem. All right, so let's talk about this. So the first way we can do it is using this composition law. So let's find our, actually, let's not use f over here because f is the name of our original function. So let's use h. So what does it make sense for our functions to be? So our inner function is 6x squared plus 7x. So I'm going to make that g. And then h is going to take it to the 4th power. So h of x equals x to the 4th. Now we're going to have h prime of g of x times g prime of x. So what is h prime of g of x? So h prime of anything, h prime of x is 4x cubed, and then we're going to plug g of x into it. So it's going to be 4 times this thing cubed. Times g prime of x. So we're going to multiply by the derivative of this, which is going to be 12x plus 7. And that's our answer. We can also do this by u substitution. So now we can let our u equal 6x squared plus 7x. And then y equals u to the 4th, right? So then, yeah. So then y is equal to exactly this, and we're trying to find dy dx. So that's equal to dy du times du dx. All right, so what is dy du? We're just going to differentiate this. That's going to be 4u cubed times du dx, the derivative of this. So that is 12x plus 7. And then we substitute in for u, so that's going to be 4 times 6x squared plus 7x cubed times 12x plus 7. Exactly the same answer we had before. And finally, here's one way not to do it, maybe. So the final way we could do this is by just expanding it out. This gets really ugly, but it is possible to do this. Here's what the answer turns out to be. And then once we differentiate using the power rule, this will give us this. So that's definitely not a great way to do it, but it does show you how much of a time saver the chain rule is. Even if it's possible to not use it, it often helps. All right, let's do another example. Let's do e to the 1 minus cosine x. Once again, I'll just pause for a moment and see if you can solve it. All right, so let's do this. So our inner function is going to be this 1 minus cosine x. So that's going to be our g. And then f of x is going to be e to the x. So that we have f of g of x equals e to the 1 minus cosine x. Now the derivative that's equal to f prime of g of x times g prime of x. So what's f prime of x? F of x is just e to the x, so f prime of x is also e to the x. And then we just apply that to g of x. So this is e to the g of x, so e to the 1 minus cosine x, times the derivative of g of x. So g of x is 1 minus cosine x, which means the derivative is just going to be the derivative of 1 is 0, that doesn't matter, and the derivative of negative cosine is sine. So that's just times sine x. So there we go. It's just sine x times e to the 1 minus cosine x. Let's do some more practice. So how about, let's do something a little bit harder. E to the 1 plus the natural log of sine x. See if you can find the derivative of this. I'll just pause for a moment and then go over the answer. All right, so let's do this. In this case, there's actually multiple things, multiple compositions. So this is going to be a little bit trickier. But let's start with the outermost one. So let's have our f be equal to this. No, sorry, let's have our g be equal to this, the inner function, and then f of x equal e to the x. So now this function here is f of g of x. And so the derivative is f prime of g of x times g prime of x. Now finding g prime of x is going to be a little bit tricky. We're going to have to use the chain rule again. But let's do this. So f prime of g of x, f prime of anything, e to the x, the derivative is still e to the x. So this is e to the g of x, which is e to the 1 plus the natural log of sine of x, times g prime of x, so times the derivative of 1 plus the natural log of sine of x. So let's find this derivative. So let's just go off to the side here. And the derivative of 1 plus the natural log of sine of x, the 1 doesn't really matter, so we're just going to do the derivative of the natural log of sine of x. Now let's just do a u sub, so we can have u equal to sine of x. And if this is y, then y equals the natural log of u. Now using the chain rule, the derivative is going to be dy dx equals dy du times du dx. All right, so dy du, well, it's the natural log of u, so that's going to be 1 over u times du dx, which is going to be cosine x. And now we can substitute. We know u is sine x, so that's 1 over sine x times cosine x. And that's cosine x over sine x, which is cotangent x. So now we can go back here. Let's move this out of our way. This derivative is cotangent x. So the final answer is e to the 1 plus the natural log of sine of x times cotangent x. And that's it. So basically we could, even though we had multiple nested functions, we could apply the chain rule multiple times to find the derivative. So let's do a few more examples. So let's just do some easier examples. I'll just write down a couple examples and then go over them. And we can maybe practice doing this without necessarily writing down the functions or the u substitution. So let's try these ones. All right, so these last couple ones might be a little bit harder, but at least the first three should be possible to do without writing down too much more than the final answer. So see if you can use the chain rule and write down the answers to these without actually writing out the functions. And I'll just pause for a few minutes and then go over the answers. All right, so basically when we apply the chain rule, we're just going to differentiate the outer function and apply it to the thing inside, then multiply by the derivative of the thing inside. So let's see that in practice. So what's the derivative of the outer function? The derivative of cosine is sine. So we're going to do sine of 3x. So this thing inside stays the same. And then just multiply by the derivative of 3x. So that's just going to be 3. For the natural log of 1 over x, so again, we're just going to look at what's the derivative of the natural log. So that's 1 over x, so 1 over x. So we just plug this into the derivative, times the derivative of 1 over x, which is negative x to the negative 2. So negative 1 over x squared. And then we can simplify this x moves up top, and I think we're left with negative 1 over x. For sine of cosine of x, it's the same thing. The derivative of the outer function, derivative of sine is cosine. So we're going to have cosine of x times the derivative of the inner function, cosine of x. So that's negative sine of x. All right, let's do the other two. These ones might be slightly trickier. So tangent of x is sine x over cosine x. For this one, we actually have to use the quotient rule, which I've mentioned once before. So this tells us that f over g prime of x equals g times f prime of x minus f times g prime of x over g of x squared. So in this case, the derivative of tan x, let me just move this out of the way, is going to be cosine x times the derivative of sine x. So cosine x times cosine x, which is cosine x squared, or we can just write this as cosine squared x. All right, minus the top times the derivative of the bottom. So minus sine x times negative cosine x. Sorry, times negative sine x. So this, in fact, this is just going to be a plus sine squared x. Over cosine x squared. And the top cosine squared x plus sine squared x is just going to be 1. So this is 1 over cosine squared x. All right, and then finally for sine of the natural log of 3x plus 1. So we're going to have the derivative of the outermost function. So the derivative of sine is cosine. So that's going to be cosine of everything inside, the natural log of 3x plus 1, times the derivative of the stuff inside. So times d dx, the natural log of 3x plus 1. So now what is this? Let's write that out. So that's going to be equal to the derivative of the natural log, which is 1 over x, applied to 3x plus 1. So 1 over 3x plus 1 times the derivative of this, so times 3. So that's just 3 over 3x plus 1. And that's this derivative here. So the final answer is going to be cosine of the natural log of 3x plus 1 times 3 over 3x plus 1. And that's going to be the final answer. So that's it for today, and next time we're going to be talking about minimums and maximums and how we can use derivatives to find them. So just as a preview, if we have some function and it has a minimum or a maximum at some point, then the tangent line is horizontal, meaning that the derivative is 0, and we're going to use that to help us find minimums and maximums. We're going to look at the derivative, and then we're going to say, okay, when is this function 0? And those are candidates for minimums and maximums. And then we'll also look at critical points and points of inflection. So basically we're looking at when the derivatives are 0, when the second derivatives are 0.